Welcome, ladies and gentlemen. We are going to begin this session, and the first paper is Impact of Load, Flow, and Controller Parameters on the Electromechanical Wave Propagation in Power System. Anatoli? Yes. Come in. Come on.
Okay, dear ladies and gentlemen, I'm pleased to welcome you to the first oral presentation at the conference. My name is Anatoli Semerow. I'm a research associate at the University of Erlangen-Nuremberg in Germany. And today I'm going to present you the theory and a small simulative study of impacts of load flow and controller parameters on the electromechanical wave propagation in power systems. So let us first look at the disturbance case in a power system, large power system. So we see here a case from 2007 for an outage of the Bendl power station, and we see in red the incident location, and in black we see the phasor measurement unit. And if we take a look to the measurements, the frequency measurements, we see that we have three stages. We have a pre-disturbance stage, we have disturbance propagation, inertial response, and the third stage, frequency containment and oscillations, which are, yes, well investigated and, yes, are very good documented in literature. So the second stage is of interest for us and also in the research in order to improve the countermeasures like power system stabilizers by communication, or use the information of the disturbance propagation for localizing the incident location and also different things. But let us first come to the theory of this propagation. So if we assume a longitudinal system with generators, we can describe the behavior of the generators by the swing equation that we can see here, here, and here, and so on for E generators. We can also describe the power transmission between the nodes by the known equations, and we can also describe the power infeed of the generators the same as the equations above. So we see all the values have a mutual connection. So if a failure appears in the system, other elements are also influenced. So for example, if we change the load demand at node 1, we can see that according to the reaction ratios here and here, we have a contribution to this to the load imbalance from the generator here and also from the other generators. And if we assume the same generators and the same reactances on the way, we can see that the generator, the electrically nearest generator, will contribute as most to the failure in the first moment. And the second generator, second most, third generator, third most. So it is the first moment. At the end, if the oscillation is over, so in the stationary state, they contribute according to the droop. But in the first stage, it depends on the reactance ratios. So if we now want to extract the electromechanical wave propagation, what is the topic of my presentation, we have to assume that the generators are more nearer at the nodes as in the case here. So we have to neglect the reactances of transformer and of the generator. And so if now a load disturbance appear in the system, only the first generator will contribute in the first moment to the load disturbance. Then the rotor angle will change due to the acceleration. And if the rotor angle changes, the angle on this line changes, and then the next generator will follow successively, and it goes on. So the speed change will propagate through the system, and the energy is exchanged stepwise. We can also see that on the next slide, in the left diagram for the usual case, where all generators contribute to the load demand, and on the right for the case where only the first generator contribute. So we can also see here the rotor angles of the generators and the speed of the generators. So we see here the case in purple where we have considered the transformer and the generator impedances, and the case where we neglected the transformer and generator impedances. So you can see the rotor angle becomes more continuous. The rotor angle is continuous at all, but the node angles become continuous also. So we can see that at the speed, if a demand occurs here, so the speed will change not at the same time, not synchronously, but successively. So this is the electromechanical wave propagation. Okay, if we would model that, we can use these both basic equations that we have seen before and model a continuum model as it was done in different publications and with online length distributed system parameters. And the result is an analytical wave equation, as we can see here. And the big advantage of this equation is that we have an explicit definition of the wave speed for the change of angle in the directions of x and y. So from this equation, we can directly see as a direct influences. These are rotor angle speed, voltage, admittance angle, inertia. And we can also derive indirect impacts. These are operational points, so load flow, and controller parameters which influence the behavior of rotor angle speed and voltage. So we have analyzed in our research all of the dependencies, but in this paper we extracted the indirect ones, and so yes, the operational points, load flow, and controller parameters. Okay, so let us take a look on the methodology. The method of the analysis: we have analyzed the dependencies in a 10-bus power system with 10 generators, each 600 MVA, and the nominal voltage of the high voltage buses is 380 kV, and each generator has control, governor, AVR, PSS, and we have minimized generator and transformer impedances to have the exclusive phenomenon electromechanical wave propagation. So we have balanced generation at each node, and we have at each node an impedance load. So also we have a switchable load at N1 to provoke such a disturbance. Okay, now we have different cases, different scenarios. We have on the one side load flow dependency with affecting generator set points or not affecting generator set points. We will see it later. And we also investigated controller parameter sensitivity. How we measure the propagation? We use a conventional method by means of an experience-based threshold, epsilon. So we define a frequency wave arrival, and the intersections of the individual frequencies define the wave arrival times, and we use the wave arrival times and the distances between the nodes to determine the wave propagation speed. This is valid for a longitudinal system. In two-dimensional systems, this should be done on the other way. Okay, there are also alternative methods available in the practice, but that they are not really practicable. Okay, let us take a look on the first scenario where we excited a load flow by impedances, so from right to left, from left to right. And if we look at the results here, we see first of all a typical characteristic of the wave propagation. So at the beginning, it is quite high because all of the power which is missing, which is switched for the load, is delivered by the first generator. So he is calibrating very steep, and afterwards he shares the power demand with the next one. So the propagation speed, flattens up, flattens down. And at the end, we have an open end, so there is no adjacent generator at the end. The last generator cannot give the power demand to the next one, so it decalibrates more, and so the speed grows again. Okay. And as we can see here, as a result of our study, is that if we assume a load flow in the direction of the propagation, we have a faster wave propagation. Okay, so here is it higher than here? And to verify this result, we have also tried it like this. So to the center and from the center, and we can see in the results that segment-wise, we have also where the direction of the load flow is with the direction of the propagation, higher wave speed than in other segments. Okay, the same we have done with affecting generator set points, so not with impedances, but with gradually increasing the generator set points. And the same fundamental relations we can also found here, but not in the same intensity due to the less load flow. And also the same with this scenario 4 we can find here, but also not the same intensity as before due to the lower load flow. So before we investigated the controller parameters, we have taken a look to this picture and keep in mind, okay, our electromechanical wave propagation is in a range of 100, 200 milliseconds. So which controller of the generator could have an impact of the propagation? And if we look at the transfer function of the controllers with the reference parameters, we can see, okay, the governor is too slow and have too small gain. And in contrast to that, the AVR is much faster and have greater gain. So the AVR and the PSS, which is also very fast, should have impact. Nevertheless, we have tried all of the parameters, and in the next slide you can see the results. You can see the results for the AVR and the PSS, also with the sensitivity factor. So you see the sensitivity is quite small, but this is valid for this reference case. So it could, in another reference case, it could be different. So let's come to the conclusion. So outlook, we have seen that we have two different phenomena in the response of disturbances: synchronous acceleration, where generators accelerate synchronously, and where the generator speed is propagating. This is a decrease propagating, so the energy is exchanged successively. This is the electromechanical wave propagation. And focusing on this electromechanical wave propagation, we have seen the load flow influences, direct and indirect, and we have analyzed the indirect ones and find out that the wave propagation speed is proportional with the load flow increase in the direction of the propagation path, what could be very interesting, especially in the two-dimensional grid where we have borders and where the wave could be faster at the border than in the center. So we found that in both cases, affecting, not affecting generator set points, and for the controller parameters, as we have seen 1-2 slides before, the sensitivity is not considerable, so they do not have considerable impact. So we hope that we contribute with our research, not only this paper, so also the other ones, to future application based on the knowledge about this phenomena. This could be wide area control and protection or event localization. So everything goes to communication. Okay, thank you for your attention, and if you have questions now or later at the coffee break.
Any questions? Any question?
Yes.
Please.
I have perhaps two questions. One of the questions, which influence has a type of generator, which you can see that you can have PV generator, you can have wind generators with power electronics connection, double fit generator, synchronous, asynchronous, and of course different control systems which can be used. Also types of control system. This is the first question. And second question, in the reality we have measured networks. It's not radial networks, measured networks. Each influence has a kind of network of your investigation. Thank you.
So we have made, the study was made by simulation. So we don't have any measurement errors. Okay. But we can also monitor the same things in the real large power system. Okay. And in the large power system we still have, thank you, we still have a lot of synchronous generators, and what I told you about the electromechanical wave propagation also concerns the synchronous generators, not doubly fed or inverter in feeds or something like that. It's always a synchronous generator. But we can talk about later.
More questions? Okay. Thank you, Mr. Anatoli.
Okay.
Okay. Thank you. Okay. The next paper, control of DC link reply eliminator with reduced capacitance for grid-connected power converters. Mr. Mijinkovsky. No? No, it's not present here. Okay. The next one, paper analysis of torque pulsation of inverter feed 5-phase induction machines. Mr. Chomat. Okay.
Thank you. Thank you, Mr. Chairman, lady and gentlemen. We have been investigating multi-phase machines or drive with multi-phase machines for a few years. Well, this particular presentation concerns 5-phase induction machine, and it is addressed the pulsations that appear in that machine due to the supply of some special voltages. Obviously, the 5-phase electrical machine cannot be supplied directly from the power grid, so we need some converter. In this case, we consider a standard voltage source inverter with 5 output phases. Unlike a 3-phase machine, which can be connected in 2 different ways, as a star-connected machine or delta-connected machine, the 5-phase machine can be connected in 3 possible configurations. These configurations are denoted star, pentagon, and pentacle connections. They differ in a way how voltages are distributed across the stator phase windings. So for the star connection, it's obviously every stator phase winding gets the supply voltage directly. If we consider sinusoidal voltages represented by these phasors, If we connect it in pentagon connection, the voltage across phase windings is only slightly higher than the supply voltage, because, well, this angle here is 72 degrees in this case. So I'm not sure exactly what's the ratio now, but you can calculate it from goniometrical equations. For the pentacle connection, you can see that the voltage across phase windings is significantly higher than the voltage from the output source. In the same way as we represent a three-phase machine in D, Q, and 0 reference frames, we can represent a five-phase machine in, well, 3 different reference frames. These reference frames are denoted in different way in the literature. Sometimes it's called DQ, XY, and 0 reference frames. We use a method of symmetrical components of instantaneous values. So we called these reference frames the reference frames of the first symmetrical component, reference frames of the third symmetrical component, and the reference frame of the fifth symmetrical component. This fifth one behaves very much like a 0 component in a three-phase machine. So it can be eliminated by not connecting the neutral point of the star connection to the ground. So there cannot develop the 0 sequence currents in the stator windings. All these reference frames or equations in these reference frames can produce electromechanical torque. So we have 3 components of electromechanical torque produced by these components, and the total torque is a sum of these components. If we look at the magnetic field density distribution in the air gap of the machine, we can see one of the advantages of a 5-phase machine over 3-phase machine. This is calculated for the same type of construction of the machine with 30 slots, stator slots, and if we use it as a 3-phase machine, well, the first or fundamental spatial harmonic in the air gap of the magnetic field density is something like 90% of what we can achieve in a 5-phase machine. So we can use the machine more effectively by making it a 5-phase machine. The other harmonics are about the same, so there is no much difference in actually higher harmonics, but we can get some higher fundamental harmonic here. For our investigation, we had a machine, an experimental machine made by a company which is producing 3-phase machines. So we actually modified the stator of a 3-phase machine, which had 24 stator slots, and we actually designed a new machine or new stator of the machine with 30 slots. So we could actually have both the machines very similar, and we calculated the magnetic field by the finite element methods. So we also calculated the higher harmonics, and you can see that there is no much difference in the contents of higher harmonics for the 3-phase machine and 5-phase machine. This is a picture of the experimental 5-phase machine, and this is a 6-phase inverter that we developed in our lab and we made experiments with. If we use a voltage source inverter for 5-phase voltage source inverter, you can get 32 different combinations of voltages at the output. It is 2 to the power of 5 So there are 2 zero vectors, well, which means that all 5 phases are either at the high potential or the low potential. And every of these combinations can be represented by a vector in the reference frame of the first symmetrical component and third symmetrical component and the 5th symmetrical component. This is just 1D, so they are just on this line, these vectors. Well, the physical meaning of the third symmetrical component can be seen from this picture. This is the magnetic field in the air gap of the machine, which is just supplied by the first symmetrical component of the voltages. So you can see that there is just one sine wave, so it corresponds to a two-pole machine. But if we supply the same machine with the third symmetrical component of voltages, we get, well, this distribution of the magnetic field in the air gap. So it actually behaves like a 6-pole machine. So at the same time, we are using the machine as a 2-pole and as a 6-pole machine. You can see the highest spatial harmonic in the air gap for the first symmetrical component is the first one, and for the third symmetrical component, this is the third spatial harmonic, which is the most salient one. Yeah, I had some animations here, but they are not working. If we simulate and measure the machine supplied in a way that we are just using the inverter as a 10-pulse inverter, we can get, well, these waveforms of voltages and currents. We made it for all the possible configurations, star, pentagon, and pentacle configurations, just to make sure that our model is working. So on the left hand side, you can see the simulation results of the simulation, and on the right hand side, you can see the experiment. So you can see that they are quite similar or nearly the same. This is for pentagon connection, pentacle connection, and this is the simulation of the torque or torque components. You can see that in all these configurations, the machine produces significant torque by the first symmetrical component and lower torque by the third component. But still, there are some pulsations from the third component which can behave like a disturbance to the machine or to some control circuitry that's regulating the machine. And which is interesting is that, well, the pulsations due to the third symmetrical component are different for different configurations. So they are most important in the pentagon connection. Usually in the literature, you can see that you need a special controller for the 5-phase machine. It's basically 2 controllers. One is controlling the DQ currents in the DQ reference frame, and the other one is actually nullifying the currents of the third symmetrical component or XY reference frame, which is quite good, but we are looking for some alternative way how to use a standard control methods for 3-phase machine for 5-phase machines. So we noticed that if you look at well, these vectors, number 25 and 16, these numbers are actually derived from binary representation of the switching of the converter. So there are zeros if the voltage in that particular phase is at the negative point, and 1 if it's on the positive point. They are in the first symmetrical component reference frame in the same orientation or same direction. They are different in magnitude, but they are in the same direction. And their representation in the reference frame of the third symmetrical component is just opposite. So here is vector 16, and here is vector 25. So if we time average these two vectors properly, we can, in every switching interval, just nullify or eliminate the effect of the third symmetrical component. So the exact ratio of these vectors was something like 61.8 and 38.2 for these two vectors. We just split the switching interval into 3 parts. Because this vector in the first first symmetrical component reference frame is lower, we also reduce the first symmetrical component of the voltage by some nearly 13%. But sometimes it's not so important for us, so we can tolerate this. So we again simulated this and measured as well. You can see that the torque pulsations or torque of the third symmetrical component was eliminated, practically entirely by now. But at the same time, unfortunately, the pulsations produced by the first symmetrical component were increased quite significantly. So we tried to split the switching interval into more partial intervals, into 6 ones. Now we can have some freedom of ordering these vectors. So we were trying different patterns, switching patterns, to look what are the best ones. So we basically moved this lower vector in a position on the first, second, and the third position. And we were looking at the results. So in all cases, you can see that the pulsations were lowest for this type of pattern, in which the lower magnitude vector was placed in the middle of the bigger vectors, which could be expected actually. So we also measured the contents of higher harmonics in the voltages and also in currents for different voltage patterns and for different configurations. So you can see that the lowest harmonic distortion was achieved by, for the second voltage pattern, and for this case, for the pentacle connection. So to conclude, we validated our numerical model of a 5-phase induction machine, and we also found a way how to eliminate the disturbance effect of the third symmetrical component on the machine. So we can actually use it also for some control schemes that are using space vector modulation. And it is possible to minimize the torque ripple by increasing the switching frequency in this system as well. Okay, so thank you very much for your attention, and if you have any questions.
Thank you. Thank you, Mr. Chomat. Any question for the presentation? Okay.
Paulo Pereirinha from Polytechnic Institute of Coimbra, Portugal. I have one question regarding your finite element simulation. Can you go back to there somewhere in the middle? Well, you have done the finite element simulation. I saw the scale of the induction. It went up to 3 Tesla, it seems. There. No, the next one, there. Okay. So my question was if your model take saturation into account.
Yes,
Yeah.
yes, this one takes saturation into account. Actually, the 3 Tesla, I'm not sure if it's...
Yeah, it's the scale, but yeah.
It's the scale. I think, well, that the highest magnetic field density in the air gap was 1.8 Tesla.
Okay.
Which for the transformer sheets that we were using data for was a little bit too saturated, but well, it was still reasonable.
Okay, okay. I was fooled by the scale because indeed it's around 2. Okay, and the results you present for the induction around the state or the air gap are from finite element solutions, yeah?
No.
The next one.
These
values?
Calculated just...
analytical?
Well, analytically, yeah. There was no saturation taken into account, and also the slot openings was infinitely small.
Okay.
Well, we had, well, the distribution of the magnetic field along the air gap from the finite element method, but I don't have it in my presentation.
Okay. That might explain some of the difference between the analytical or the simulation results and the experimental ones. Okay.
Yeah, actually, well, these finite element methods were obtained by my student just, I don't know, maybe a month ago or less than 1 month ago, so I didn't have time to incorporate it into my presentation entirely.
Okay, but thank you very much. It was very interesting.
Okay, thank you. Another question? Okay, thank you, Mr. Chomat.
Thank you.
Thank you. The next paper, Intersystem fault in multi-circuit overhead transmission line of different voltage and frequencies. Mr. Novitskiy. Okay, thank you.
So, ladies and gentlemen, my name is Novitskiy. So, I'm from Technische University at Ilmenau in Germany. I am glad to present you some results of our investigations in the field of intersystem faults in multi-circuit overhead transmission lines, different voltage and frequencies. Short overview of my presentation, some word about intersystem faults, equivalent circuit diagram for the analysis, network for the analysis, simulation of the intersystem faults, method for the estimation of the energy list, calculation result, and summary. Intersystem faults in multi-circuit overhead transmission lines are well-known effects and can be classified in several typical cases. For example, one of them is combined 3-phase lines. We have multi-circuit lines, the same frequencies. In this case, we have 380 kV 4-circuit lines, in double circuit 110 kV lines with 50 Hertz, the same frequency. Second case, typical case, is combined AC-DC transmission line, hybrid three-phase lines we have. In this case, double circuit 380 kV transmission line and DC line, HVDC line, plus minus 500 kV with metallic return, for example, which are well known. This case of the study, which I would to present, is concerned with combined 3 and 2-phase AC lines. It's also multi-circuit lines, but in this case we have different frequencies. Actual task for the Germany, Austria, and Switzerland. We have for the railway supply the frequency 16.7 Hertz, also with 110 kV is high voltage line. In this example is a real pylon with double circuit 380 kV line and double circuit 110 kV line with different frequencies. The effects of an intersystem faults by a multi-circuit transmission line different frequencies is based on the relations of impedances, on the change of the impedances with the change of the frequency. The line, which is designed for the operation with 50 Hertz frequency, has, of course, higher, smaller reactances for the frequency 60.7 Hertz and higher capacitance for the 16.7 Hertz. It means that if you have a contact between 16.7 Hertz network and 50 Hertz network, the currents from 16.7 Hertz network go not to through line capacitors, but mainly through line impedances to the Rs, low ohmic Rs, usually used by 380 kV networks with 50 Hertz operation frequency. Other one is the effect of the impedance change for the currents of 50 Hertz in the 16.7 Hertz network. It means we have smaller impedances, for 50 Hertz network, higher impedance, it's more capacitances. It means if you have contact, direct electrical contact between 50 Hertz network and 60.7 Hertz network, the current goes to the earth directly from line capacitors or goes through the network to other phase. Of course, the impedances of Petersen coils, which is presented in German 60.7 Hertz network, were also higher, third time higher for the currents of 50 Hertz. This is effect. For the simulation study, this is a real part of 110 kV network with many segments which contains different lines of different frequencies and voltages on the same pylons. Length of multi-circuit overhead lines used common pylons are noted in bold times. Let's see some. The biggest line, 26.2 kilometer. We have 380 and 110 kV line. But the problem is, as I saw already, we cannot determine the parameters of 60.7 Hertz directly from the line impedances, line capacitance for 50 Hertz, because the real impedances of the network are depending on the load states operating, on the network operation, on the load operating states, on the weather condition, and so on. From this point of view, for the determination of parameter equivalent parameters of 16.7 Hertz network, was carried out in measurements. And one of substation of 110 kV 60.7 Hertz network. So, it's measured equipment has measured the change of the voltage on the point and the change of the current at the measurement point. This Semerow method, well known for the estimation of the impact from an individual distortion sources for the determination impedances of each part of sources. We can do these measurements at each point of the network. We divide our network on 2 parts and can calculate equivalent impedance. So we have one line, double circuit line 1, line 2, both circuits, connected to substation 110 kV, and we said all this supply we supplied through this line is system 2, and all other things are system 1. Have measurement, have down the measurement, and you can see the change of the impedance, equivalent impedance for 50 Hertz in the network 110 kV, 60.7 Hertz. It's dependent on the loading, of course. It's a change over during the week, but if we take into consideration statistical values, statistical distribution, we see that for all phases of the 110 kV network, we have very similar, practically the same values of equivalent impedance for the frequency 50 Hertz. So we can take value for the impedance for its average value, 50 Hertz, 50% quantile, and minimal values. That can do the calculation if we considered the measured values in our models. So here are some simulation results. These green lines are intersystem fault currents, intersystem fault currents, 50 Hertz, root mean square values, independence on the fault position, A, B, C, or D, and so on, and independence of the value of equivalent impedance for 50 Hertz in the 110 kV network. You can see that this impedance has decisive role for estimation of the value of an intersystem fault current. And it can change from less than 2 to over than 4 if we take into consideration different values of equivalent impedances. So we have not so important, not so big influence, not so significant influence on the impedances on the value of star point voltages and some in the intersystem fault position. But the value of the star point voltages, 50 Hertz voltages, is 16.7 Hertz network are over 200 kV. And this 16.7 Hertz network are designed for the operation with 110 kV line-to-line voltage. It means more than twice in some cases. Effect is known from that. From experience, we know that by such contacts, sometimes Peterson coils in 110 kV networks will be damaged and destroyed. There's a reason for it. For estimation of the energy released by intersystem faults, was suggested to take from simplified estimation the method which used in standard to calculation short circuit currents for the estimation of thermal equivalent short circuit current. It means it's not only initial symmetrical short circuit currents will be considered, but also the influence of DC components, which is always occur during the fault. Choose factor for far from generator short circuit can be this one factor, I think one equal 1 according to the standard. For factor M, there's a standard curves from the source. Must be calculated as duration of short circuit hour, and for frequency 50 Hertz, we receive 7.5. Without consideration of without detailed knowledge of the R2X relation is network, we can take the worst case M1 equal 1. So we receive squared from 2 and can calculate according to common formula intersystem fault energy. Intersystem current is initial symmetrical short circuit current, residual voltage, star point to, not star point, fault point to ground voltage, and duration. So we receive values of the release energy which can be released from it. We have sometimes, by some situations, the values of the energy or 320 MVA a second. For conventional high voltage surge arresters, with some standard values, 15 kilojoules for each kV. It means if you take 1000 kV, multiply with 15 kilojoules each kV, we receive only 15 megajoule. Okay, here we have also not megajoule, megavolt amp a second, but because it is common energy which can be released in general case, if we take active part of this energy, perhaps it will be 10% from it, but 10% from 320 megavolt amps second is anyway over 30 megajoule. It's twice as more as 15 megajoule. It means also theoretically that our surge arrestor will be destroyed. It cannot protect our Peterson coils if we have an intersystem fault in such situation. And here's for comparison the calculated values, residual voltage, and the fault locations were also practically the same as line to ground voltage in 380 system, over 220 kVs. So, short summary, we have taken an analysis of intersystem faults in multi-circuit lines, different voltages and frequencies. It was shown that harmonic impedance of the network has a significant influence on the characteristic of the intersystem faults. First of all, significant influence on the characteristic of intersystem fault current. It was shown novel simplified method for the estimation of energy released by an intersystem fault was suggested. It was shown that estimated value of the thermal energy which can be released by an intersystem fault can be significantly higher than the energy capabilities on conventional high voltage surge arrestor. It means that must be done some special measurement for protection of the network from such possible cases. Some current limiting devices, some better protection, quick switching off, and so on. So thank you for your attention. I'm ready for your question.
Okay. Thank you, Mr. Novitskiy. Some questions? Some questions? Okay. I have one question. Here in Canary Island is not normally the different frequency for the electrical system, but now exists the possibility of electric supply for the ship, the port,
yes, sure,
with different frequency.
Sure.
Okay. All this is the application for this system?
Of course.
Of course.
Of course, because important here, so must take into consideration both impedances.
Yeah.
For the operating frequency and for frequency which can be used by other systems.
Okay. Okay. Thank you very much. Okay. The last paper is Supercapacitor modeling by Lagrange equations. Thank you. Mr. Vitale.
Okay, good morning, ladies and gentlemen, and thank you in advance for taking this presentation. I hope you enjoy this presentation. My name is Gianpaolo Vitale. I'm with the National Research Council of Italy. The This contribution is titled the Supercapacitor Modeling by Lagrange Equations. So in this paper, a model of a double-layer capacitor based on the Lagrange equations is proposed. The Lagrange function for the equivalent electric circuit is obtained by the generalized charge coordinates. The model is then implemented in Simulink environment, and simulation results are compared with the experimental test performed on a commercial supercapacitor of 83 farad at 48 voltage of rated value. The fundamental of the presentation contains an introduction, a description of double-layer capacitor fundamentals, a description of an equivalent model of the double-layer capacitor, then the Lagrange function for electric circuits with the consequent Lagrange equation for the double-layer capacitor, and a comparison of experimental and simulation results. Why we are studying supercapacitor? Essentially for maintenance, since the possibility to store a high quantity of energy implies a possible risk for which maintenance has to be operated. So it's crucial to have an idea, better possibly on a model, of the rating of the system, so to provide a substitution, for example. And it is expected maintenance before breakdowns. It's very, very dangerous in this case. So, as it is known, a high value of capacitance can be obtained by a reduced distance between the plates and increasing the area. Double-layer supercapacitors allow to obtain a very, very virtual area. This gives us the possibility of extremely high power capabilities, up to several kilowatt over kilograms, and many life cycle up to 1 million. Here we can see in few words the history of increasing capacitor from traditional to electrolytic capacitor, in which there is a very thin dioxide. But in electrostatic double-layer capacitors, by the Helmholtz double layer, an interface of a conductive electrode is obtained, and there is a very, very small separation of charge. This is the order of 0.3, 0.8 nanometers. So this allows to reach this high value of capacitance. But I have to say that this very short distance implies very high electrostatic field. So the voltage is crucial, the rated voltage. For this reason, ultracapacitors are located with a value of energy density higher than capacitor and lower compared with traditional storage system. But they are very, very interesting in the range of time of several seconds, contrary to capacitors that are operated for smaller times, and traditional electrochemical storage system operated in time of about 1 hour. There are many interesting applications in the field of power electronics. For example, vehicle system, for example, for regenerative braking. Since in this case there is need to store electric power in a short time with a very high current. So it's crucial to have a storage system which is able to manage so a high current. Another example is the start module for a vehicle. We are used to find in a modern vehicle the start-stop system. This is can be useful performed by supercapacitor rather than an electrochemical battery.
To find in a modern vehicle the start-stop.
But there are many other applications. For example, in weak grids, a storage system made of supercapacitor can be used to lessen the drop voltage due to the lack of inertia of rotating generators and so on. But when you charge this kind of capacitor with a constant current, differently from a traditional system, the voltage profile is not a straight line. It is a quadratic curve. So from this, the necessity to implement different modelization of this kind of capacitor. In this kind of model, mainly used for high power applications, the nonlinearity is modeled by a capacitance made by a constant term and terms which depends on the voltage. So this is a nonlinear behavior. In addition to this leg, there is a traditional linear leg with a pseudo-capacitance, but the value of this capacitance is lower compared with the main capacitance and the leakage resistance. It is important, this kind of modelization, to know or to estimate, it's better, the value of parasitic resistance and of this kind of capacitance. Because in case of aging, the end of life can be detected by the knowledge of the parasitic resistance and of the nonlinear capacitance. In particular, a common criteria to establish the end of life is to an increase of 100% of the parasitic resistance and a decrease of about 30% of the main capacitance. So this approach uses the principle of sectionary action. This is a variational principle that, when applied to the action of a mechanical system, can be used to obtain the equation of motion for the system. That starts from the definition of action, in which the Lagrange function contains the kinetic energy and the potential energy. But why this kind of approach? It is interesting since often supercapacitors are used in cooperation with the mechanical system. So it is possible with this approach to obtain the overall equation of the system, including mechanical quantities. According to the principle of stationary action, if a generical coordinate q traces a path through the configuration space, the path taken by the system has a sectionary action under small changes in the configuration of the system. So the system going from Q1 to Q2, in principle, could trace infinite way configuration, but the nature chooses only the configuration which corresponds to the stationary action. Assuming as coordinates the charge and the derivative, it means the current, it's possible to write the Lagrange function containing, in principle, the coenergy of inductive elements and energy stored in capacitive elements. But in this representation, of course, there are only the contribution of capacitive elements. And a dissipation function which represents the losses in parasitics and leakage resistance. So we obtain the classical, canonical representation of a Lagrange equation for the electric circuit in this case, in which there is an equation for each coordinate. In this approach, there is need of three coordinates. The first two represent the charge stored on the two capacitance, so they are the state variable, and the last is the leakage current on the leakage resistance. So of course, these three terms are constrained by the supply current. So in this way, it's possible to calculate the derivative of the Lagrangian function with respect to 1, 2, and the leakage coordinates, and obtain this equation. So this is the model obtained by the Lagrange equation. It can be noted that it is a non-linear representation, so it does not correspond to the traditional set space approach. This equation can be implemented in several ways. Of course, it can be discretized. For example, this is an example of implementation in Simulink environment. I am showing this since the interest is that it's not necessary to calculate derivatives. It's possible to implement the equation so that the charge is obtained as an integral of the current. So in this way, the calculation of noisy derivatives is avoided. In order to compare the results obtained by the model and a practical situation, a test bench has been prepared with a supply system, and supercapacitor for automotive application, and two kind of load to perform a free and forced discharge. This is the supercapacitor proposed by the Maxwell. It is a supercapacitor with a rated capacity of 83 farad. Let's note that the parasitic initial resistance 10 milliohm. So this system is able to manage maximum continuous current of 100 ampere, but the peak current can reach about 1000 ampere. So very interesting for power applications. This is the current used for the test. So we charged the supercapacitor with a different profile, starting from 5 up to 40 ampere. So the supercapacitor is charged up to its voltage, reaches the rated value. Then, for a period, is not charged, and after this, a forced discharge is performed. Now we can compare experimental and simulation results. This is the charging phase and the discharging phase. It's interesting to note the shape that corresponds with the quadratic curve, and on the contrary, the forced discharge is an exponential curve, very similar in all cases. Here we can compare the relative error. During the charging phase, the model shows an error always lower than 3.5%. The error is higher during the discharging phase, but we should note that this error is computed, I go back, with very low values of the voltage, so it's not so relevant. By the model, it's possible to calculate the current even if they are not directly measurable in each leg. So it's possible to observe that the main current is managed by the first capacitance, the aggregate capacitance, and in the current managed by the pseudo capacitance is lower, and this is the current due to the leakage resistance. So these are the steady variables. I remember you that from this result it's possible to have an idea of the supercapacitor aging. As a matter of fact, we perform the measure on a capacitor in which the capacitance is lessened due to the continuous charge-discharge operation. We can note that with the same current, this is charging with 40 amperes, we note that the voltage is higher with some quantity of current. So an aged supercapacitor operated with some current will have a higher voltage could be dangerous since the electrostatic field inside is extremely high. So we can go to conclusions. A two-branch model of supercapacitor based on the Lagrange equation has been developed. The use of a Lagrange equation allows additional terms, as for example, the energy coming from a mechanical system to be easily accounted for in the Lagrange function. This implementation does not require a circuit simulator, obtaining a reduced computation time. It is able to reproduce the current and the voltage at the equivalent capacitor terminals. I wish to emphasize the last term, since it is not so easy to implement nonlinear components in a traditional simulator. So in this way, it's possible to avoid the use of a circuit simulator, obtaining a very fast computation time. And this is all. Okay. Thank you for your attention.
Thank you, Mr. Vitale. Any question? Okay.
Thank you very much. Well, you compared, thank you for your presentation, you compared the experimental results with the simulation, and I didn't understood very well your errors, because from can you put back that slide on the errors? No, that one. So what is the difference between the chart on the left and the chart on the right?
Okay. You can note that the time. Oh.
So it's.
I go back. Okay. This is a charging and discharging phase. So this error is referred to the charging phase.
It's yeah.
The last part from 1,200 seconds to 2,000 seconds is calculated on the discharging phase. So this is a zoom of this part.
For the discharge, okay.
So this is the error from 0.
The charge and discharge phase, okay.
So this is a zoom of the first part.
Okay, and I have another question. You have currents up to 40 amperes, yeah. But on the photo with the experimental setup, okay. What was the cross-section of the cables that you were using? It seemed quite thin cables for a current that might reach 40 amps, and where the contact resistance might have some influence on the contact, and the cable resistance can have some influence on the results.
Nice question, thank you. In this case, an appropriate station have to be used, since the parasitic resistance is very, very small. So the traditional criteria of 5 ampere over square millimeters is not appropriate. So we have used about 10 millimeters of square for the section. But it's not so crucial, the cable, but the connection between, because the contact resistance could be higher, especially if the planar of the surface is not so respected. So there is need, if one wants to estimate the parasitic resistance, to have a good electrical contact between surface over the supercapacitor. I will show you.
Yes.
Okay. Not so. This is the terminal of a supercapacitor. This is not the setup used, only a photo to show the supercapacitor, in which the terminal have to be mounted with a very accuracy.
So it's not that one that is shown. Okay. Okay, that's it. That's my question.
And in practical measurement, this need of a short electrical connection. This is only to perform some measurements on supercapacitor.
Thank you.
Thank you, Mr. Vitale. Any question? No more question? Okay. So we finish this oral session. So now is the lunch time. Okay. Thank you very much, everybody.